Thank you very much. Yes, I am a little bit excited because we had so great talks today, although I haven't heard yours, but it sounds very interesting. And what I'm trying to do here is trying to bind things together. I don't know if I will achieve that. And I have thought that maybe it might be a good idea to start with a controversial, offensive idea. And that would be that there are many misconceptions actually in robotics, and I would like to address 3 of them. And of course, I'm pretty sure that you will tell me, well, that's not the way robotics is, and you're certainly, it's certainly also true. But I think many of these misconceptions, I think they are, at some level, they are there. And so that's why I like to address them. And I will go through each one of them. Actually, the 3rd one is the smallest one, so don't be worried when I am talking for a long time. For the 1st and the 2nd one, that's fine. The 3rd one is really not so big. Okay, so I will just jump into it. And I think the first misconception I have always thought was really weird in robotics is when you talk, I mean, and you are roboticists, many of you think, I don't know, you can correct me, but I think many roboticists think robots should learn autonomously because they don't want to be bothered with interacting with them and so on. And when they can learn autonomously, they can incorporate tons of data and they can learn really more than even humans can. But actually, when you look at it, it doesn't necessarily make so much sense. Because when you look at it, for example, when we look at how humans learn, and humans learn incredibly efficiently. So when you look how we are doing it, and we have seen what Katharina also has presented. So human infants, they learn through interactions. And the reason why this is so important is because some actions cannot be learned through observation and imitation alone, because there is a meaning to them that you cannot observe. And maybe you cannot observe even what the goal is, because it's not always visible. Maybe you don't see really the means, how things are being done. Maybe there is haptics involved that oftentimes you cannot see. And so the meaning of an action in terms of goals or means or also the restrictions that are there need to be communicated by a tutor. And currently, robots are not capable of incorporating that into their skill learning. And there is some evidence, of course, that when we look again at humans, of course we are able to reason about actions and trying to understand what's going on. So this is from Chibra and Gergely, who have really done a lot of studies with children and have looked at their way of understanding actually the goals of others. Again, as far as I'm concerned, I would say in robotics, goals, while they are necessary, they are often not incorporated in the way of reasoning about other person's actions. So children primarily imitate causally efficacious means to achieve goals. We will see in a minute what that means. They ignore apparently unnecessary actions. So when you have a robot that performs imitation learning, the robot will imitate no matter what, right? It will not interpret what it's imitating. And unless the demonstrator makes it manifest for them that these cognitively opaque aspects are relevant. So the ostensive behavior of the tutor is important. We have already heard about that. And so what does this mean? It means that when we observe an action, we may observe some kind of behavior. We can track human hands and so on. We can maybe even observe the end state, although we don't even know which part of the end state that is there is now actually the relevant part, right? And we can observe maybe the physical context, but still we don't know exactly what it means. And so the interpreted action means that we really understand what was actually the goal of this end state, what was really the means that brought about this goal end state, and what were the constraints. And so the idea is that actually, and that children already at a very early age are able to do this, exactly this. And so let me present, this is just the favorite experiment, and I like it very much. So in this experiment, there were very small children, 14-month-old children. It was sort of a teaching situation. And so there was an experimenter sitting in front of, so there a table between the child and the experimenter, and there was this strange button in the middle of it. And after some kind of course, familiarization, the experimenter would hit the button with her head. Okay, so really doing this kind of thing, a really weird action, right? And so, however, there were two different conditions. In one condition, you can see this, her hands were lying on the table. But in the other conditions, she was sort of holding a blanket. And so these are two conditions. And what are your expectations? How did the infants react? Any ideas of that? Yes?
So if the hands are free, I think they would learn to do the action like the person does it with the hand. But if the hands aren't free, they infer that they actually can do this with their hands, because it's not the head that's important, but just the action.
Exactly. Great. So you have, yes, you got it right. And that's exactly what they did. And but there is one thing they did before that. Before all of this imitation, they really emulated. So emulation means that you try to bring about the end state with the fastest means that you have, and that is actually all of them really did press the button with their hand. So that's the first thing they do, and only then some of them really imitated the head gesture. So well done. And it's true that only in the, well, not only, but when the tutor's hands were free, 70% used the head. When the hands were occupied, only 20%. And so that's exactly that. And this is, apparently there is this kind of really rational thinking going on when very small children imitate actions. And so we see here again, in this situation, there was no specific support. So that there is the capability, of course, of infants to infer goals and means and constraints. But again, they infer this, of course, also again in a social situation, and they know that this is a person which has goals that might be similar to the ones of the child. And of course, the goal that was achieved, namely that the button actually was lighting up, was an interesting goal for the child, so you have to make it interesting and so on. There was a certain sociality about this, but nevertheless, you could argue, well, this was done autonomously. However, there are other studies, and these are the studies that Katharina already mentioned earlier on. So when we look at how parents really teach actions to their children, we see a lot of ostension going on. So ostension really means we try to exaggerate things. And ostension is, for example, motherese or caretakerese. So when you talk to children, really your voice goes up and down. And your prosody is really very special, so you try to get interest and so on. There's a similar thing with motions. So when parents show things to their children, they will exaggerate motions. They will make it higher, slower, leave more pauses, and so on. And this is something that we have investigated a lot with mothers and fathers. I just want to show you very briefly just a couple of results. And so here, actually, there were 10 items. For this study, we just investigated these ones because they are a little bit similar. There are always 3 objects that need to be put somewhere. So they have a certain similarity in action. In a way, they are goal-directed actions because the action depends on where the object in the end is. And so we wanted to see actually the relationship between, actually wanted to see what parents actually do when they interact with the children. And so we actually analyzed in an objective manner the gestures, the movements of the children, not of the children, sorry, of the parents, of course, when they were demonstrating these actions, actually not only to their children, but also to their spouse, so that we also have adult-directed actions from them, so we could compare that. And I won't go through all of these, but we tried to get something like the action length, so just the duration of an action, velocity, acceleration, range. For example, we tried to measure how far you deviated from the direct path, right? Because when you're quick and you don't want to demonstrate something, you go quick. But when you want to demonstrate something, apparently you, as we will see in the results, you do some kind of range movement that can be described with this variable range. So we had several of those, and we investigated that, and we found, of course, that many of these parameters were changed in infant-directed actions. However, we wanted to find out, because as Katharina already told, when you talk to little children, they need a lot of attention getting. So you need to guide their attention, right? Because they are distracted very, very easily. So they might be really interested in what you're doing, but then 2 seconds later, they might be interested by something else. And so you need to get back their attention. And so we thought that many of these things that we have seen, we didn't know which of these features actually were related to this attention getting and which of those were actually related to the semantic action structuring part. And so we wanted to look at this in a longitudinal way, because we thought that actually younger infants, right, they need more attention getting, whereas older don't. So maybe if we see features that are there for younger children but not there for older children, then those might be the attention-getting features, and the other ones, the ones for structuring. And so we did that, and we ended up really with the results that there are actually just a few attention getters, and exactly actually this roundness and range, they are attention getters, apparently. So they are there for younger children, but not so much for the older children. Whereas other things like the pauses, or the pace, which actually is a relation between movement and pause duration, they seem to be the structuring elements. And that is actually pretty well to interpret, because apparently you make pauses, and this relates a little bit maybe to what Michael said this morning, that in actions you can have a segmentation, maybe depending on certain dynamics. I don't remember how you called them, but I think it was related actually to the dynamics of the action itself. And we don't know yet actually if this corresponds to what you're saying, and that would be interesting to see. But we see at least that there are pauses in the actions when you demonstrate them to the children. What we don't know is how they relate. So what we did then, and also we didn't know how does the speech, and which contains the semantics, right, relate to the action itself. So what we also did was then we looked at the concept that actually a long time ago already was coined by Rebecca Brand, and it's called acoustic packaging. This is actually synchrony between speech and actions. And so what you see here is her experiment. So these are the stimuli she created for the children. And so you see actually actions she's doing. So an action A, where she's looking at the bottom of a bottle. Action B, I don't know, she's doing something at the top of the bottle. Then again A, and I think in C she is turning the bottle. And so in the familiarization, so children are shown over and over again these videos so that they get familiarized with it. However, and always in this sequence, A, B, A, C. However, she would sort of package, and that was the hypothesis, package this sequence A, B with an audio, so with speech. And this would, of course, be Mother Reese. And so the speech said, "Wow, do you see what she's doing? She's blitzing." Okay, so really trying to get the attention and so on. And it would just take the duration of the action A and B. And the hypothesis was that this would bind it together. And so then in the test situation, she would show actually a split screen. So and on the left side, the children would see A and B, and on the right side, they would see B and A. So the same things, but in the other direction. And we know now that once the children have been familiarized or habituated on AB, that is the idea of this kind of method. Then they, of course, they are bored by that and they want to look at the new thing. And so when they are now preferring something, that would indicate that they will see it as something new. And so what happened was exactly that. Even though they had seen B and A, right? They had seen B and A exactly as many times as they had seen A and B. What they would do, actually they would see B and A as something new. And the idea was that this, or the interpretation is that this is because the action was packaged by the speech. And so this appeared to be a completely new action. Okay, so I think this is amazing, and it's really interesting that we have this kind of packaging because it allows us to segment tutoring input into meaningful segments. That's at least the assumption. And so we tried actually to model this. This is actually work by a former PhD student. And so what he did was actually he used this motionese data that we had, so these explanations of the parents to the children, and he looked at the acoustic channel. And he tried, of course, to segment that by finding pauses there and finding also pauses in the movements with very actually low-level features. And then he had a temporal association of these two input streams, and they would then result in what he called acoustic packages. Okay, and so he ran this on the data that we have of the motionese corpus, where we had actually he looked at 11 dyads, so 11 adult-adult interaction and 11 adult-child interactions, the same adults. And actually, we had another study where we also had 11 adult-robot interactions, just to see what happens. And the analysis was done with these acoustic packages. And actually, we wanted to know how many packages are in one action demonstration, and then also what is the mean number of motions per action package, right? So you can have a package, but within this package you can have different motions that are packaged together by speech, right? Because if you speak long enough, you can put a lot of different motions in there. And so the hypothesis was, of course, that child-directed speech is more structured than adult-directed speech or interaction, and we would find more acoustic packages and less motions in ACI. And this is what we found, and it's indeed exactly what we found. So here you see the green bars are the number of acoustic packages we found in one sort of instruction. And you see that in adult-adult interaction, we have like two acoustic packages per task, so to speak. In the child-directed interaction, so adult-child interaction, we have 4. And this is very interesting. In the robot-directed interaction, it's even more 6. And I think one of the reasons is that the robot was really slow in following, so the gaze was very slow. Yeah, that might have caused that. And we see, on the other hand, the number of motions per acoustic package, and I mean, that's also clear, but of course it goes down because it's structured more. And so it goes down from 3, well, to 2.5 to 2. And so you see really that there is really less complexity in an action demonstrated to a child. And so this is really great news, because when you want to learn from these data, it should help you, right? Because you get really smaller entities that are less complex. And that is something that should work better. And so the unsolved questions that we haven't addressed so far is, of course, is learning faster because of the tutoring, right? Because that would be what a roboticist would ask me. Yeah, but if you tutor them, then it has to be really faster. But is that really the case? We would have to look at that. But the other thing I think that is probably even more important is how do the motionese features actually enhance the semantic knowledge? And do they do that, the motionese features, or how do the semantics, so the speech that is accompanied by that, how do they actually enhance or transfer the semantic knowledge, like the goal or the means or the constraints? And that is, I think, something that we haven't done so far. And I think what you're doing here in your fall school, right, you are doing a lot with semantic representation and reasoning. And so using this kind of software that you're using here, or I think that could help a lot in doing such things. So I find it really interesting what's going on here. Okay, so that was my first misconception that I would like to address, and you can really get back to me on that. You can answer me on that and can tell, no, that's not so. But I would say robots shouldn't learn only autonomously, right? Because also it's humans, and I hope you have seen that, we humans, we have something I would call like a teaching stance. So when we are faced with a robot that is trying to learn something and we see that it can't achieve it for whatever reason, I think what we then do is two things. One thing, if possible, and if you are afraid, probably we would try to touch the gripper and try to push it in the right direction. It's something we would call scaffolding. And the second thing is we would try to explain. Okay, do it faster or slower. Oh no. Whatever. Okay, so we have this intuition to do that. But the robot doesn't let us, and I think that's sort of disappointing. And we should not disappoint the humans who want to teach robots, I think. And one of the reasons, again, is I think that learning by teaching is probably a lot faster. There are a lot of, arguments in favor of that, right? I mean, humans have developed language in order to transport knowledge that has evolved in humankind, so to speak, and so that we can transfer knowledge to our offspring. And so there is a lot of good arguments in there that the language, the way we have structured is really helpful for us in our everyday activities, actually. Okay, so that was the first misconception. Second, interaction is just for giving commands, okay? So if I want to speak to my robot, I just want that the robot does what I tell him, okay? So cut or slice the cucumber. However, again, if the robot can do it, that's fine. But again, we see that interaction is, of course, bidirectional. And we know that especially now when we are sitting in Zoom meetings and we see the black tiles of people who don't want to put on their cameras, it's really hard to talk to black tiles, really. You don't see anything. And it's really great when you have people, some of you are nodding, and that is really, it's a great help for the speaker to see that. So and interaction is always bidirectional. Even if there's somebody like me who's talking all the time, it's still bidirectional. And not just that, the feedback, and especially in a tutoring situation, the feedback of the learner is really, really important. And it sounds so easy and simple, but yeah, it is. And so one of the things we have done is, this is actually, again, work from other people, from Anna-Lisa Vollmer and also from Carola Pietsch. And what they did was they actually looked at the gaze of the child while, and here we finally have a father, demonstrated an action. And we encoded this in colors. And here the colors are actually, so red, I don't know if you can see it even, but red means that the gaze was away, okay? So, whoops, sorry. That the child wasn't looking at the object. And so what we see here is the father is really lifting the cup and waiting until the gaze comes back to the object. And then he's moving the object to the target position. And I think here the blue means actually this is anticipating gaze. So the child is already, okay, it's going there. And then the gaze is faster than the cup, actually. Okay, so you see that there is a very close relationship between the demonstration and the feedback of the child. And so the action demonstration is built on monitoring the learner's feedback, and the learner shows the understanding and the knowledge of the action with the feedback. And in this case, it's the gaze. And anticipating gaze at a certain point is, of course, a sign of understanding already. And so the traditional approaches of action learning in robots actually tended to be that you have a tutor who demonstrates the action, and then the action knowledge somehow gets back to the learner. But it has always been thought of more or less like a one-directional thing, right? You demonstrate it, the robot records the data, and then it will learn. Actually, it can happen that you never see the finally learned action itself because it's done in simulation or whatever. So that has, in the beginning, never been thought of. However, if you really want to have a good interaction, you need to get back and take into account the feedback of the learner and see to what has it learned and what is the action it's currently carrying out, so that I can, as a tutor, help and explain what is still missing. But before we can do that, we wanted to know actually how does the robot learner's feedback affect the teacher's action demonstration. And so here, again, this is a work by Annalisa Vollmer. We looked actually at different kinds of action. Actually, we looked at goal-directed actions versus manner-directed actions. So actions where it matters where the object in the ends up, that's a goal-directed action. Whereas manner-directed action is like when I have a sponge that has to be moved in a certain way, or a feather that is flying in a certain way, then the path or the manner is the important part of it. And we also had different kinds of feedback. So the robot could either demonstrate emulation, so just trying to copy the result, which would go well with the goal-directed action, or imitation, so like copying the path, let's say, which would go well with a manner-directed action. And also we had some kind of online feedback, a following gaze, so a gaze that follows really the object, a random gaze, and a static gaze that just looks at the tutor. And again, so we have these different interaction actions here. So, and emulation would mean that when you show whatever kind of manner, then the robot would just find the shortest path between the start and the end point. Whereas in the imitation, it would really imitate the path it has recorded. And just so that you see what it looks like, here you see actually, so this is supposed to be how a feather is falling, and she's really doing it very nicely, and you see really the slow movements, and also the way how she puts it down, right, like the real feather. And now you see these are actually the just a copy of the recorded coordinates. But you see already the movements are somehow a little bit different. They are not so smooth. And now this is interesting because, boff. Yeah, so this is important feedback, right? Because it tells you there are things the robot just can't do. Or maybe it can, but it doesn't know. But yeah, some of the people really got overwhelmed by this kind of feedback. Okay, and sorry, and then we have here the gazing feedback. And it's a little bit painful to look at because it's really slow. So this is now a sponge being moved. And you see how slow the robot is following it. And again, you see the close coupling. Normally you would do it faster, right? But you're really waiting here for the feedback of the robot. Okay, so this was the online feedback that we gave. And I like this one. It looks a bit like he's also relieved that it's over now. And so again, now we try to, we measure the tutoring behavior, again with the same variables and features we used before. And so here are some of the results. So maybe here, so this, we just here investigate just the first action demonstration without actually already taking into account the feedback. And what we see, for example, is that, for example, goal-directed actions are encoded differently than manner-oriented actions. I mean, that's a little bit obvious, but nevertheless, it's there. So, for example, the range when you have a goal-directed action is very small, but when you have a manner-directed action, you tend not to do it that way, but you tend to do it sort of really in a different way. So that was one of the results here. So the teachers encode their action knowledge in these demonstration parameters. Interestingly, also what we saw was that here we see the number of repetitions. So as a tutor, you could say how often the robot should repeat. So, I mean, it's just every time you as a tutor show something, the robot will repeat, and you can decide how often you want to demonstrate. And so in the imitation case, actually, you got significantly less number of repetitions as compared to the emulation case. This is just regardless of goal or manner directed. And this already indicates that apparently imitation is preferred. And we see that both in the manner and the goal-directed situation, the imitation received just the same amount of repetitions, but the emulation received really a lot of, requests to do it again. And again, so what it tells us is even the correctly emulated goal-oriented actions, these ones, are repeated more often than the imitated ones, which is interesting. But it might be, of course, because the robot doesn't have really the capabilities as the human has, so like the feather which is dropped. So that is there. But we see that imitation is preferred by human teachers, which I find is an interesting result also here. And we also see the term-based feedback. Oh yeah, when we look at the eye gaze, the different kind of eye gaze, and we see the velocity, for example, and this is very clear, right? You have seen that the social one where we follow the object, and because the robot is so slow, it decreases the velocity a lot as compared to random or static. And also, accordingly, the action length inversely is changed. So the social behavior of the learner also, in a way, it yields a better learning input, because if it's slower, you have more time sort of to find, to see it, and you get more data, actually. Okay, so we see that feedback is important for the teacher to adapt. And so this is the second misconception of robotics. And I'm good in my time, right? I'm really great. And with this, I would now like to come to the third thing, and here I have to agree that this is not completely true. Okay, a stable representation has to be a static representation. This is not entirely true. If you look at navigation, for example, in SLAM, I think people know that representations can be incrementally built up. Okay, but oftentimes, if you look, for example, at imitation learning, what people want to do is they want to get data, and then they want to train the model, and then that's the model. That's the model of cutting, or of pouring, or of whatever, and then it's there. However, it shouldn't be that way, because the way we learn is, of course, that we can continue to learn and make things better, or adapt them to a certain situation and to a certain context. That's really important for us, that we are capable of adapting. And so a robot needs a stable representation in order to act in its environment. That is true, of course, in a sense, but it doesn't have to be really static. And representations are really emergent, and they are shaped through interaction. And now I would like to look at the other side, and this is just this, actually a thought experiment, even not an experiment. So consider teaching a robot an action. So now consider the same situation we have just seen, but what should be the representation actually of the robot of the action demonstration? So imagine you want to show how the frog is moving. Of course, it's useless, but nevertheless, you want to show that. You do the action demonstration, and that is, but however, the robot maybe only samples at these points. Well, then the robot will, of course, come to a wrong representation because it will try to get these points together. It only has recorded these 3 points. It will get this. So it will do the action imitation like this. And so the teacher, what does the teacher do? Well, supposedly the teacher will modify the action and will try to exaggerate the movements. And miraculously, and I don't know how, but actually the robot would need to have some kind of facility to see that somehow there is an action modification there. Of course, if it still has these 3 points, sampling points, it won't be able to recognize it. So that there need to be, of course, other, and that's actually a real problem, right? So currently, when you do this learning stuff, you have features. You need to have enough features, and normally what you do is you end up with too many features, actually. So because then you try to sample, I don't know, so often that you have a lot of redundant data. That is probably the more realistic thing to look at it. And then out of all these huge data, you have to find out the ones that are relevant, and that is really, really difficult. And so this is really miraculously that the robot, in this case here, he has now detected that there are different points to be detected, and then can change really this representation. And that's just the idea that I want to convey, that a stable representation in the teacher, right? So the teacher has a stable representation of the action he wants to demonstrate, and still this can lead to variable action demonstrations, because you want to emphasize certain parts of it that you'd think the other one didn't get or didn't understand. And so the learner's representations also need to be flexible, to be incrementally built up. Okay, thanks. And yeah, and also the increment here would also be that, I mean, there was already part of it correct, right? So this movement up, that was correct, but you just have to repeat it 3 times. So this would be sort of the incremental learning part of it. And so, yeah, representations need to be flexible in the way that you really can incrementally build on those. And as you may have seen, actually, I have here now talked a lot about skill learning, which is a little bit different, right, from the task learning that is often done, or I think that is also targeted when you're dealing with knowledge representations and reasoning, like you're doing here, I think, in the fall school. But I think we need to bring these two things together so that skill learning really becomes something meaningful for the robot, so that the robot really understands what it is doing with a certain skill, also in terms of knowledge representation. And with this, I'm ending my talk. I'm looking forward, maybe, hopefully, to some of your questions or critical remarks that you don't have these 3 misconceptions I never have had. But yeah, thank you very much. And I tried to do it. In the local dialect.
In time.
Also in time. Thank you.
So, thank you for this great talk. So, are there any questions? Okay, I have to ask. Do you think we, as a robot or robotic scientist, do we need to think more about inductive and deductive teaching? Our robots?
Yeah. What would you mean with inductive teaching and deductive teaching?
Yeah, well, giving an undefined or a more undefined task to the robot and tinkering, and the robot should tinkering out what is to doing, or should we say, okay, this is a task, do it like that?
That's a good question. Okay, I think I understand where that also might come from. I think that's something that is also done in pedagogy these days. That you want that the children should learn by exploring themselves and finding causality themselves and so on. And I think yes, that is certainly also important. But my and my point would be, but to put something on top of that. I think it's not sufficient when you just let the robot explore or the infant explore. It will only come to a certain stage, but then it will need some input. So some kind of semantics in order to better understand what's going on, yeah.
Okay. Yeah. This is what I expected, yeah. So, any further questions? Of course.
Thank you very much. You showed very much application or examples where the robot is the learner in some sense. And but a lot of the things you have investigated could be very interesting also in if roles were switched. So when the robot needs to teach, or even when the robot needs to explain myself, maybe itself. So I was wondering whether you are thinking on how you could leverage on these kind of information, let's say motionese, motorese, or other also kinematics information, and balance that with other forms of explanation to make it more effective? Well,
that's a very good question. Actually, it's yes, in a way we have. I mean, we have Katharina speaker now of the Collaborative Research Center on constructing explainability. So explaining, yes, is in our view. We haven't currently so much in the... I mean, we know that multimodality is very important. The current focus there is more on more abstract things to explain. But you're right that when you want to explain actions, then you would exactly need these things, but we haven't done that yet. But it's sort of, yes, the logical next step actually to do. Yeah.
Thanks.
Okay.
Thanks for the talk. I had just one question about feedback from the student, right? So when the teacher is teaching some new or novel task or action, what sort of feedback you think a student can provide so that a teacher can still understand, okay, this part is solidly understood by the student. Like for this human children, it's quite obvious, right? They can emulate, or they can also talk and express themselves freely, but what about robots?
Yeah, that's a difficult thing, because we don't know and we don't understand robots so well, right? Because they have a different learning mechanism, and the feedback that they give, it might be engineered, and then it will not tell us perhaps really so much. Or it might indicate, it might be, for us, we might not be very well equipped to understand that feedback. And that's really another problem. And so, yeah, actually, we have a project dealing with that, so that the robot is capable of giving feedback that helps the teacher to provide the right input, so to speak. And so, yes, so and the idea behind that, yeah, would be to investigate how good is the input of the teacher for my learning model. And if it is good, and I sort of proceed, and my measure, whatever that is, gets better, then apparently the teacher is doing well and understanding well. But if it's not, then maybe I, as a learner, have to provide some kind of other feedback. Yeah, and I think that would be different from the feedback that children give.
Sure. Yeah.
Yeah.
And also, I mean, from robot's point of view, they should be able to say, sorry, I can't do this, right? So
Yeah.
for either emulation or for imitations, they have some restrictions. So they should also say that this part of the imitation I can't really do, right?
Yes,
From
but yeah,
whatever constraints.
that would be great, but that would already require meta reasoning, right? They would know and have to know that they cannot do this. So, for example, the robot needs to understand that for some reason it cannot go below a certain threshold and so on. Yes, yeah. But it would have to make that explicit. That's not so easy. Yeah, definitely. But yeah, I think that would be a great help if it could communicate this. Yeah, definitely.
Hi. When learning from demonstrations from humans, for example, VR demonstrations, so in virtual reality, you notice often that the demonstrated tasks lie somewhere on a spectrum between goal-directed and manner-specific. So some things, the way the human moves, are actually essential to completing the task. For example, collision freeness. If a human keeps avoiding obstacles, that's quite important for many tasks. Yeah. Or if contact is kind of kept between two objects, if things are slid, important for some tasks. But for other tasks, that's completely like, just because the human decides to do it that way, completely irrelevant to the task. So how do you have an intuition as to how we can maybe use the kind of mutual communication between teacher and student to make these aspects of the task which are important specific?
Speech?
Well, yes, I mean, sure, right? But it's also ambiguous in many ways. So, or have you tested this in experiments, or you know?
Yeah. No, not yet. But it's definitely. So I think it's one of these crucial things, because you need to know which of the features you are referring to. So it's actually the reference problem again. You need to know which part of the feature. What does it mean to I don't know, to be very close together, or to not touch, or to touch, and to learn that. I think that's that's. I have not the answer to that. Only that with these, with all these features that we have seen, that if you are good at finding those, at least you could know that there is some issue here that is important, and then at least you would have a cue that you have to search for something. Now in the action that has been done here, because apparently there is something important that I missed as a robot. Yeah. So I think, so far. And then a co-construction loop would sort of have to start and be initiated, perhaps with trial and error or so. And also, I mean, human-robot interaction is not human-human interaction. It's really different. And maybe we need an additional interface where the human teacher can see what the perceptions of the robot are. In that case, maybe even the haptic perceptions, and then you can say, oh, yeah, this one, I think this one is the difficult stuff. Mm-hmm. Yeah. Cool.
Okay. So now we have to wait until the break starts. No. Okay, I think, thank you very much for your great talk.
Thank you very much.
We have a lot of new ideas and some of our misconceptions. Thank you very much. So, I will open the door and the coffee is outside. So, okay.